All right, guys, today's lesson is on what we would call hybridized orbitals. You guys think about that word hybrid, right? You probably think about like a Toyota Prius, and what's a hybrid, right? You guys know it's a combination of a combustion engine and a electric car, right? So it's kind of a blend of the two. That's what hybridized means. And so what we're going to see here is electrons don't always exist in just in an s orbital. You remember as a spherical orbital, or p orbitals, which are dumbbell-shaped orbitals around the nucleus, but when involved in bonding, some of those orbitals hybridize into a blend between the two. That's what we're talking about today. So anyways, it's got this advertisement that says missing. Little strip of paper with phone number on it. So this has phone numbers on it. It's missing. Okay. So we think of covalent bond, we're talking about sharing of electrons. Remember, that's what covalent means, right? Two hydrogen atoms, each which have a one valence electron. They need two in order to be happy, fat, content, stable. So what will they do? They will overlap their orbitals and share each of the one electron from both, and therefore, as if two valence electrons are orbiting each nucleus. Think about a hydrogen with a chlorine atom, right? You have a hydrogen's electron is in a 1s orbital. Chlorine's valence electron's in a 3p orbital, right? So it'll have one electron here in the 3p orbital. Unfilled orbital, and also hydrogen has an unfilled orbital with one electron, and what will they do? They will overlap, and then those two electrons will both orbit the chlorine nucleus and the hydrogen nucleus, thereby making both of them happy, fat, content, stable, and likewise two chlorine atoms. Right, so this is what we're already are used to seeing. Okay, so we're not seeing hybridization yet. It can only occur when orbitals on the two atoms overlap, and that just means that the electrons are orbiting both nuclei, and that's essentially what we're talking about when we're talking about covalent bonding, what holds those nonmetals together. So you guys can see, just imagine, right, we have two independent atoms, and there's a relatively high energy state, and as those atoms get closer together, so it's showing them get closer together, the potential energy decreases. It reaches a lower, remember that's the ideal, the lowest potential energy state. And then there's going to be an ideal separation between the atoms, where the nuclei are ideal distance between each other, or from each other, such that you have the place of lowest potential energy. And that's how you would expect the bond to exist. And you can see if the atoms, however, got even closer together, all of a sudden the potential energy shoots up, and you can imagine why. Atoms can only get so close together because at some point, right, the positive nuclei from both atoms are going to begin to repel each other to a point where it's going to be unstable. And that's what this is indicating right here. So now we're going to talk about a new situation where orbitals hybridize. So this is our s orbital, right? We have p orbitals. Remember, there's 3, x, y, z. Okay, those are ones that we typically look at. So now, for example, consider a beryllium. Okay, so this would be the electron configuration for beryllium. Beryllium has 4 electrons. You look on your periodic table. It's always good if you guys have your periodic table available. I'll try to show it to you occasionally, but it's easier if you guys can refer to it. It's got 2 electrons in the 1s and 2 electrons in the 2s. But if you look like at this point, it looks like there's no unpaired electrons, but we know experimentally that beryllium tends to form 2 bonds. So how is it going to form 2 bonds? It has these empty p orbitals and it has filled s orbitals. So what they realize is if a little bit of energy is supplied, right? You can just imagine as atoms come in contact with each other, with just a little bit of energy, right? The 2s orbitals are slightly lower in energy than the 2p. Well, wouldn't you agree if it absorbs a small amount of energy, one of those electrons from the 2s orbital can be bumped up to the next lowest potential energy level, which is the 2p. Now you'll see in this case, there are 2 unfilled orbitals, which could help explain why it forms 2 bonds. But what you'll find when it forms 2 bonds, it doesn't form a lower energy, it doesn't overlap with a lower energy 2s and then separately another atom's orbital overlap with a 2p. What they find is you actually have 2 overlapped orbitals of equal energy. What we call that is they must have hybridized. And so that's what we show here. One of the s orbitals and the p orbitals combine together. See that the s and the p here kind of combine together. Rather than having a separate s orbital and a separate p orbital, you guys see there's 2 separate orbitals. What you'll find is you're going to have 2 orbitals of equal energy. And so those will hybridized, you guys can see this is what we call the hybridized orbitals of an s and a p orbital. And what do we call it? It's pretty simple. We call it an sp orbital because it was a hybrid of an s orbital and a p orbital. That's called an sp hybridized orbital. So rather than one s orbital and one p orbital, we have two what we call sp orbitals. That's essentially what we're saying. So beryllium, right, would form like we just showed you, where the electron is bumped up. The s and the p orbital hybridized. Now we have two sp orbitals, one electron in one sp and another sp, and then what's it going to do is going to overlap in this case with fluorine, and then the valence electron from fluorine, one of the valence electrons from fluorine in its 2p orbital overlaps with the the sp orbital from beryllium, and these show that way. In that way, they're both happy fat content stable. And you guys remember from BSEPR, we would expect this to have a linear shape. As you have sp orbitals, there's two sp orbitals. Remember, they're going to maximize separation. How can they do that? 180 degrees. It's a linear shaped compound. So you guys see what we did, right? One of the s's and one of the p's hybridized together, and now we have two sp hybridized orbitals. And you can see the sp are slightly higher in energy than the 1s orbital, but they're slightly lower than the energy of 2p orbitals. So they're hybrid between the lower 2s orbital and the 2p orbital. Okay, so now look at boron. Boron would exhibit hybridization as well, because you guys can see, based on, this is the electron configuration for boron. It's got 3 electrons, this is the valence configuration. A lot of times we'll just show the valence, right? We're not going to show, boron actually has 5 electrons, right? You have 1s, but then in the second, the outer shell is the valence electrons, and it would be 2s2, 2p1. Based on this, it would seem like boron would only just form one bond, because it only has one unfilled orbital. But once again, what could happen? One of the electrons from the 2s orbital with absorbing a little bit of energy can be bumped up to the 2p. And so now we see we have 3 unfilled orbitals. But once again, what we find experimentally is that you don't have one orbital of lower energy and 2 orbitals of higher energy, or electrons in those of higher energy. What you find is 3 electrons of equal energy, thus indicating that they must be in the same type of orbital. So what must have happened is these 3 unfilled orbitals must have hybridized, kind of changed form a little bit, right? Where the electron is orbiting, it's slightly different spatial arrangement around the nucleus, into what we call sp2. You guys see why it's called sp2? Because in this case, it's 1s orbital hybridizes with 2p orbitals. And so what do we have? We have 3 what are called sp2. See how you can get it? There's 1s and 2 p's. That's going to make 3 sp2 hybridized orbital. And then we still have, you guys see, we still have the empty 2p orbital there. Okay, so this can help explain when we have boron. So here we've got 1s and then we have the 2 p's. And when they hybridize, you can see it's kind of like a mix between the s and the p's. We have 3 orbitals of equal energy. And so, okay, now another one that frequently hybridizes is carbon. Look at oh wait, did we already do this? Okay, so carbon. Look at the valence configuration for carbon. Why is it doing that? You see it's got, if we see this, and you guys, we should know this, carbon is unique. Remember, carbon is the one element that's common in all organic compounds. What is it that's unique about carbon? Remember, it forms a lot of bonds. It forms 4 bonds. You guys should see that based on its placement in the periodic table. Well, what could explain that? If this is the valence configuration of carbon, it looks like it could only form potentially 2 bonds. What can happen, once again, this could be bumped up. So now we have 4 unfilled orbitals, but what you would expect those to do is hybridize, once again, into 4 what are called sp3. And you see how you can get it? There's 1 s orbital with 3 p orbitals, so that would be for 4 sp3 hybridized orbitals. And that's what we would expect carbon to form, depending on how many atoms it binds with, and we're going to look at that here shortly. So you guys, I know this is probably hard to see on your end, but what this is showing is if you have a linear arrangement, it's going to form an these are going to be 2 sp hybridized orbitals. If it's a trigonal planar arrangement, right, a central atom down to 3 adjacent atoms, those are going to form 3 sp2 hybridized. And your typical tetrahedral like CH4, right? Methane, carbon, for example, bound to 4 hydrogen atoms. That would be 4 of your, that's a tetrahedral, that would be 4 sp3. And then it even gets a little more complicated. You can start incorporating d orbitals. Now, if you had 5 in this trigonal bipyramidal arrangement, it would be sp3d. And then if you had 6, it would be sp3d2. So they're starting to hybridize even d orbitals. But you know what? I just want you guys to remember the sp, sp2, and sp3. If you guys got that, I think we're good. Okay, let's see if this helps us.
In the 1930s, Linus Pauling introduced the concept of hybridization to explain chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals
let's look at sp.
Mixing an s orbital with one of the p orbitals generates 2 equivalent sp hybrid orbitals. Note that the number of hybrid orbitals is equal to the number of atomic orbitals that are hybridized. The set of 2 sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees.
So you guys, what they're saying is, right, you notice we started with an s orbital and a p orbital, 2 orbitals, and when they hybridize, it's formed 2 separate sp orbitals. So you still end up with the same amount of orbitals that you had before, they're just hybridized to blend between the other orbitals. So sp2.
Mixing an s orbital with 2 of the p orbitals generates 3 equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of 3 sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees.
And then sp3, guys, we would, just for sake of time, that would be tetrahedral, right? With a central atom, particularly carbon, bound to 4 other atoms. So the priest here, the pastor says, love, honor, and cherish, those being too lofty a goal, do you promise to simply look up, nod, and pretend to be listening? And the dude said, huh? Oh yeah, sure. Hopefully my male students, you're not going to become like a husband like that. That's just not good. Sorry, ladies. You want to avoid people like that. All right, valence bond theory. Hybridization is a major player in this approach to bonding. 2 ways orbitals can overlap. Okay, guys, so this is what we're finishing the last major topic for today. We have what are called sigma bonds. And you're like, dang, is this another new thing we got to learn? Sigma bonds. You guys really, if you did think about sigma bonds like single bonds, you'll be all right. So a sigma, that's from the Greek letter, that's the sigma. Looks like an O with a little tail on the end. Sigma bonds. Sigma bonds are really head-to-head overlaps. So you guys remember what we were saying is, in a covalent bond between nonmetals, orbitals overlap, and so that way the electrons can orbit both nuclei, and that's what holds the atoms together. So if you think about it, the 2 hydrogen atoms, the 2 s orbitals, they overlap this way. They're going head-to-head. Think about it like that, head-to-head. Or think about with the formation of hydrogen chloride, you got the valence electron of hydrogen is an s orbital, the valence electron in chlorine is a p orbital, but even then, the s orbital and then a p orbital, those overlap head-to-head. We would simply call that a pi bond. Okay, so it's just a different way to say the same thing. And here as well, 2 chlorine atoms, both p orbitals, if they overlap head-to-head, that would be called a sigma bond. But not only can orbitals overlap head-to-head, they could overlap side-to-side. And here you guys see, rather than the 2 p orbitals, overlapping head-to-head, they're overlapping side-to-side. That is called a pi bond, and so that's the Greek letter pi. We already know that. That's a side-to-side overlap. And you guys are going to see this is what we would associate with double and triple bonds. So you guys are going to get an idea and see what this looks like.
Let's examine the bonding in 3 molecules, ethane, ethylene, and acetylene. Click on one of the molecules to view an animation of the bonding in that molecule.
Hey guys, this is good because they show you the Lewis structure, and then you can see from that what kinds of bonds would form. Okay, so here's ethane.
First, consider the Lewis structure of ethane. Counting the number of VSEPR pairs of electrons around carbon 1, we find 4 VSEPR pairs. You should also count 4 VSEPR pairs around carbon 2.
So some things that I would expect you guys to predict at this point based on what we just learned, we would expect, right, there would be kind of like a tetrahedral shape around each carbon. You guys see, because there's 4 things it's bound to. And then we would expect the hybridization to be sp3. How do we get sp3? Well, just think, 1s and 3 p's make for 4 hybridized orbitals. So we'd expect it to be sp3 hybridized.
The VSEPR model predicts that the geometry about each carbon atom is tetrahedral. In valence bond theory, 4 sp3 hybrid orbitals have a tetrahedral arrangement. We can begin to explain the bonding in ethane if we assume each carbon atom is sp3 hybridized. Each hybrid orbital will contain 1 valence electron, accounting for the 4 valence electrons of each carbon atom.
So guys, ethane is a simple hydrocarbon. You guys see it just contains carbohydrate. Just to kind of make it real, you guys, this would be like a component of gasoline. Gasoline would have a lot of different sized hydrocarbons. Okay, just
The bond
continue.
formed between the 2 carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei.
You guys can see why it's called a sigma bond, because those pi orbitals, sp3 orbitals, they overlapped head to head. Now, if we look, obviously this hasn't met the octet, right? At this point, how many valence electrons does each carbon have? 1, 2, 3, and then the 2 that are being shared. So it's got 5 here, and this has 5. Obviously, what are we missing? Obviously, we still have the hydrogens, and so you can imagine the hydrogens would overlap here.
When we add the hydrogens, the remaining 3 sp3 hybrid orbitals on each carbon form sigma bonds by overlapping with hydrogen 1s orbitals. 2 electrons are shared in each sigma bond. A single bond is composed of 1 sigma bond. Lastly, rotation can occur about a single bond because rotation will not break the carbon-carbon bond.
Okay, so you guys, a good way to think about it, if you guys have single bonds, like you remember the Lewis structure, you're just thinking, oh, those are all sigma bonds. Because that's the first type of bond that's going to form, is an overlap of the orbitals. Okay, you guys, let's look at one that has multiple bonds. We're going to look at ethylene. We'll look at ethylene here. Acetylene, by the way, that's a gas. You can see they're all hydrocarbons, and you can see we're getting less hydrogen. So what you're thinking is, oh, rather than single bonds, we might start incorporating double and triple bonds. Acetylene, by the way, is a hot burning gas that you actually use for flame torches. You have it's called an acetylene torch. But we'll just go with the ethylene right now.
First, consider the Lewis structure of ethylene. Counting the number of VSEPR pairs of electrons around carbon 1, we find 3 VSEPR pairs. Recall that double and triple bonds are counted as single bonds in the VSEPR model. You should also count 3 VSEPR pairs around carbon 2.
So you guys, at this point, I would expect you guys to be able to draw the Lewis structure, right, just from the number of valence electrons, and you guys should come to the result, in order for the octet rule to be satisfied, you have to have a double bond here. So this accounts for all the electrons, that's the Lewis structure. And then, you guys, we should be able to even predict what type of bonds would we expect to be around this carbon here, at least for the singles. Where you look, that each carbon is bound to 3 separate other atoms. Well, you're thinking 3, you're like, oh, that's probably what kind of hybridization? sp2, right? Because that's going to form 3 equal orbitals sp2.
The VSEPR model predicts that the geometry about each carbon atom is trigonal planar. In valence bond theory, 3 sp2 hybrid orbitals have a trigonal planar arrangement. We can begin to explain the bonding in ethylene if we assume each carbon atom is sp2 hybridized. Each hybrid orbital will contain 1 valence electron, meaning that for each carbon, we have accounted for 3 of its 4 valence electrons.
So you guys see how it was called trigonal planar? We'd expect trigonal planar because you've got 3 things bound to the center atom, and what's the best way that 3 things could orient themselves around the center point? Remember, they want to maximize their separation because electrons repel. You guys remember it's trigonal planar, it'd be like a Y shape. But you guys can see it like that. Okay, so then you guys are thinking, what are these going to do? Aren't these orbitals going to overlap? That's what kind of bond? Wouldn't you guys agree? A sigma bond.
The bond formed between the two carbon atoms is called a sigma bond. A sigma bond is a covalent bond formed by orbitals overlapping end to end. The electron density is concentrated between the nuclei of the bonding atoms. In this sigma bond, 2 electrons are shared between the carbon nuclei.
Okay, so obviously we're missing the hydrogens, guys.
When we add the hydrogens, the remaining 2 sp2 hybrid orbitals on each carbon form sigma bonds by overlapping the hydrogen 1s orbitals. 2 electrons are shared in each sigma bond.
So you guys see, is this the right Lewis structure? You guys would agree. You should see no. Look, each carbon only has 2, 4, 6. 2, 4, 6. So, but you guys have to remember we're actually missing. So they're kind of doing this in steps. You remember what we're missing is that double bond. So we're going to see what that double bond looks like, because there is actually, each carbon does have, you remember it had 4 valence electrons. We only counted for 1, 2, 3 here. It has that, and those went into sp3, but then it also has an extra electron in a p orbital, unfilled p orbital. So we're going to see p orbitals, and we're going to see what happens to those p orbitals.
There is still one more bond to explain. Which orbitals overlap to form the second bond of the carbon-carbon double bond? Recall that when sp2 hybrids are formed, a pz orbital does not mix to form the hybrids. Each carbon atom has a 2pz orbital, perpendicular to the sp2 hybrids, that contains the 4th valence electron.
Look how they're going to overlap. You guys think about how are those going to overlap head to head? Those are going to overlap side to side. What do we call that type of bond? That's called a pi bond.
The 2pz orbitals can overlap in a side-to-side fashion. This type of covalent bond is called a pi bond. The electron density is concentrated above and below the plane of the nuclei of the bonding atoms. In a pi bond, electrons are shared. In other words, the 2 electrons are free to move through both regions of the bond. A double bond is composed of 1 sigma bond and 1 pi bond. Lastly, rotation does not occur about a double bond. For rotation to occur along the carbon-carbon bond, the pi bond would have to be broken.
Okay, so you guys heard, hopefully you heard that. So the double bond, you guys see how it's sharing 2 pairs of electrons, so that's a double bond. A double bond involves a sigma bond. You remember that's always the first bond. And then it's going to be a pi bond is going to be the second one to make for the double bond. You guys a little bit more. So single bonds are always sigma bonds. Okay. And then when you have a double bond is going to be a sigma bond first, and then 1 pi bond. And then if you had a triple bond, like with N2, you guys remember the vast majority of all the air in the consists of nitrogen. And why is there so much nitrogen in the environment? Well, you think about it's a triple bond holding it together. Those are very hard to break, and so as nitrogen builds up, it's hard for it to break down. So a triple bond would be a sigma bond, and then it'll have 2, p orbitals overlapping for 2 pi bonds, therefore making 1 sigma bond and 2 pi bonds. So you guys, just to kind of show you what's going on here. So look, just because I think it is kind of hard. Just think about carbon. Okay, so carbon. You guys, I'm going to do the valence electron configuration of carbon. Right? Here's carbon. It's got 4 valence electrons. Right? So it looks like that. Once again, we wouldn't expect it to form 2 bonds. In fact, what we do see is 4 bonds. In typical fashion, carbon forms 4 bonds. So what would we expect to happen? We'd expect there to be, right? We'd expect one of those electrons perhaps to jump to a higher energy level. So one of those jumps. So now I've got, what do I have? Oh yeah. You see, and it would just jump, this would jump to here, right? So you have this. But you guys can see the carbon's only bound to 3 separate things, right? Oxygen, hydrogen, and hydrogen. So what happens is only 3 of these hybridize. So one of the S's hybridizes with 2 of the P's, and what do you form? sp2 hybridized orbitals. But you notice it was just the 3, so we have 1 electron in each of these. And so that's what's forming here, right? That's an sp2 hybridized, sp2 hybridized, sp2 hybridized. But then what do we still have? We still have this 2p orbital with 1 electron. You guys see, and that would be the electron here, and this one has the same. So what those end up doing is those will end up overlapping side to side, and that is that second bond, the pi bond that makes up the double bond. All right. And then, when we showed with acetylene, here's acetylene with a triple bond. And you guys, I don't want to do this whole thing again. Or you know what, I could. So how does a triple bond form? So we can have the same thing. How are we going to do this? Yes. The only difference is, so we have the same thing here, right here, because you remember carbon's going to form 4 bonds. But in this case, you notice each carbon is only bound to 2 things. This carbon's bound to a carbon here and a hydrogen here. So what kind of hybridized orbital would I expect? Just an sp. So it would just be 2 of these will combine to form 2 sp orbitals. Okay, and so that forms an sp orbital here and an sp orbital here. But then what does it have? It still has 2 separate p orbitals, each with 1 electron. So this would be a p orbital here, so an electron here and electron here, and then those will overlap to share those 2 electrons. And then it also has another p orbital on another axis that can overlap side to side. So what do we have? We have a sigma bond, and we have 2 pi bonds for a triple bond. All right, last thing, guys, just want to remind you a little bit of resonance. You guys remember, if you're doing a Lewis structure like NO3, nitrate, you guys see that's got a minus. You guys notice if you can draw it another way, well then that would probably indicate it has different resonance structure, right? Is there any reason why the double bond should be between this nitrogen and this oxygen and not this one or this one? In reality, it can be between any of those. And in reality, the electrons in the double bond here are not localized just between this nitrogen and oxygen, but it can be delocalized between all of them. We talked a little bit about this. So this is kind of showing the overlap of the pi bonds here, but there's nothing to say that those electrons can't overlap here or overlap here. And in actuality, that they would be kind of blended between all of them. Remember, we call that resonance. Like if just imagine it, the electrons are moving and they're sharing between here, sharing between here, sharing between here. So it's going to be, so what they find is the bonds are going to be the same length between all these oxygens and nitrogens, indicating they're all the same bond. We say that that's delocalized. So we talked a little bit about this in the last video lesson. And you guys remember at the benzene ring, we talked about alternating single and double bonds. And you remember when you get to OChem, they're not even going to show the carbons. There are actually carbons on all these vertices, and then hydrogens attached, we just don't show it. And so the double bonds can alternate between, and so we would end up writing it like that. Once again, an example of resonance. So showing the double bonds here, showing the double bonds here. In actuality, it would be a blend between all of it. All right, guys, that's it for today. Thanks for tuning in. We'll see you guys next time.